Who knows Tim Head? Does this ring a bell? Oh, wow. Few people know him already. Not many. But he's a maintainer of scikit-learn, and which is a machine learning library. And he also worked on building and running mybinder.org and JupyterHub. Who has used JupyterHub before? Okay, some people. Who has used mybinder? So if you use JupyterHub and have like Jupyter notebooks, you can just run them in a Docker container on mybinder.org to have like a ready available data to explore for other people. Yes, he already attended a previous conference in 2018, and yeah, and now he will talk about when approximate is good enough, and with a deep dive into probabilistic data structures like Bloom filters, or maybe not so deep, I don't know. So now, please welcome Tim.
Hi, my name is Tim, and in my normal life, I work on a lot of open source projects. But today I'll talk about Bloom filters and other probabilistic data structures, which I learned about probably 15 years ago for the first time. And at the time I thought it was almost like magic, that what these things were doing. And this talk, hopefully at the end of it, you don't believe that it's magic, because there is no magic involved. But you have a feeling for how they work, when you might want to use it, and things like this. So I spent a lot of time while preparing this talk thinking about some kind of opening joke about when close enough is good enough, you know, Switzerland, the land of precision, things like this. And I couldn't come up with a good one until this morning. I was sitting in the train and I was wondering why there were so many people looking so stressed. I was like, surely you're not all speakers at the Swiss Python Summit. When we arrived at the next stop, I understood why they were all looking so stressed, because the voice that announces which station you're at was off by 1. So we left Stäfa, and when we arrived in the next station, it said, nächster Halt, Stäfa. I was like, I understand why you're all stressed now. So sometimes close enough is not good enough. No, you have to get it exactly right. Okay. Maybe probabilistic data structures is something that doesn't tell you anything. So I'll quickly talk about what exact versus probabilistic means for me. Exact data structures, I think all of you know, things like lists and Python dictionaries and sets and things like this. And if, for example, you have a set, you insert an item into it, and then later query the set, and ask, do you contain this item? You get the answer yes, with 100% confidence. And if you query for an item that is not in the set, then you get the answer no, this is not in the set. For probabilistic data, or maybe you're counting how many different types of fruit are going past you, and you're using a counter to do that, then you will get exact true answers for how many bananas, how many oranges, etc. Probabilistic data structures, on the other hand, you might have something which works like a set, and then when you query it, the answer is maybe yes. Or if you have a probabilistic data structure to count items, then it will give you a number, but it's an estimate, and it might be off by a few percent. So that's the difference between exact and probabilistic data structures. I'll talk about 3 today. Bloom filter, maybe a lot of you have already heard or read about before. Count, min, sketch, and something with the most amazing name, if you ask me, HyperLogLog, which is crazy because it's actually, a super fancy name. You want to use it just because it has that name, right? So when you export your slides as PDF, you don't skip the slides. Okay, so what could we do? We could have the task of keeping track of items, and the simplest possible way that we could probably build this in Python is to make a class like this that uses a list as an attribute, and when you add a new word to the dictionary, then we add it to the list. And if you then later want to query, does this dictionary contain this word, then we check whether the word is in the list. so far so straightforward. So when you then use it, you load words into it, and then later on you do check like is hello in the English language or is ciao in the English language, and you get the correct answer. But imagine you live in a time long before today when computers had a lot less memory. So now there's about 200,000 words in the English language, so you need, I don't know, a few megabytes of memory to store all of the words. And a long time ago, computers only had a few megabytes of memory. And so maybe you don't want to spend 2 or 3 megabytes on just implementing the spell check. And you have to build a whole word processor. Alternatively, in today's age, now of course we have 2 megabytes to store all the words. This is not a problem, but there's still problems out there where there's so much data that the amount of memory you have to work on it is tiny compared to the amount of data. Also, depending on whether you want to be retro, then pretend your computer has no memory for the next few slides, or if you are, looking towards the future, then imagine you have a very, very big data set. So even when you rent the biggest machine on AWS, the memory is tiny. So the problem, if you don't have enough memory to keep track of all your items, is that it doesn't fit into memory. And the obvious solution is, well, don't store all of the words. Then you don't need less memory. And the cool thing is about the word tracker, we don't need to be able to recite all the words that are in the dictionary. We only have to answer the question, is this word in the dictionary or not? Which means we don't have to actually store the words. We don't need to be able to tell you what the words are. You come to me with a word, and then I tell you yes or no, this is in the English language. So what we could do is we could make a big array of bits that uses a lot less memory, set it all to 0. And then we compute the hash of a word that we want to insert. Then we go to the right index in the array and we set it to 1. So now when you come to me and you ask, is the word hello in the dictionary, I compute the hash, I go to the right index, and if it's a 1, then I say, yes, this word is in the dictionary. And if it's a 0, then I say, no, sorry, this is not in the dictionary. And then we insert the word by, and so on and so on. And now we're not storing the words anymore, and we use a lot less memory than before. And one thing to quickly talk about is hash functions. So they're one of the key ingredients to building all these probabilistic data structures, or for very many of them. And the simplest possible one that you could build is something like this. Now, what it does is it takes a string that, no matter how long it is, turns it into a single integer. So you can have one word, you can have a whole sentence, you can have a whole book, you compute the hash of it, it comes up with a single integer. One way to do this is to just go through all the characters in your string, compute that, or look up the ASCII value for the character, sum it all together, and then do modulo some big number to make sure that it's not bigger than the array that you have. And you get, arbitrary long strings turned into integers. You could probably give a whole lecture series on hash functions, and I will not do that today. There's very many of them. How to design them is super interesting if you're into that kind of stuff. The important things for us today is you can use them to summarize inputs into a single integer. Similar inputs create very different outputs. So if you compute the hash of the word hello with E, you get, 42. And if you compute the hash of hello, so you change E to A, just one small change, you get a hash which is completely different. You don't get like something that's close by. And the other useful thing is that we can make a whole family of hash functions. So which means you have maybe 5 different hash functions that you apply to the same word, and they produce 5 different integers. Now, those interesting features for today, and then you can maybe propose a talk for next year to talk about all the other intricate details of hash functions. If you've been thinking ahead a little bit about our word tracker, our dictionary, you might have figured out that there's a problem. Two different words might end up using the same index in our array. So in this case, the word bye and ciao happen to use the same one. And now that's where this is maybe more like a probabilistic data structure, not an exact one. Because really, when you ask me, is the word bye in your dictionary, I can't say, yes, it is in the dictionary. I can just say, maybe yes, because it could have been that the word ciao is the reason that there's a 1 in this index. So I can say definitively, no, this word is not in the dictionary when the entry is 0, but when it's 1, then I can just say, maybe this is a word in the English language. So that's illustrates the point, the big difference between using a list where we keep track of every single word and we can definitively say yes and no. Here we can say definitively no and maybe yes. The implementation for this is not much more difficult than what we did so far. We have a big list of zeros, then we compute the hash of the word and go and set the index to 1. And the check for membership is the same. And you use it exactly the same. Okay, so what is a Bloom filter then? A Bloom filter is exactly what we already built. Now, most Bloom filters use multiple hash functions, and I will explain in a second why that's a good idea. But what we built just now is you can sell it as a Bloom filter. And the idea is that you can use it like a set. Now, if you use it if you want to keep track of things that you've seen. And a great thing about Bloom filters compared to using a classic set is they use vastly less memory. Not just a factor 10, but a factor 100 or a factor 1,000 less memory to keep track of items. And the price you pay is that you can't say definitively yes anymore. You can just say maybe yes. And if you want to implement it, it gets a little bit more involved. The important thing is now that we now iterate over our n hash functions and set n entries to 1, but otherwise it works exactly the same as our simple word tracker. So one thing that will happen is eventually your Bloom filter is full. Now imagine you make an array of 10,000 entries and you try and put 200,000 words in it. All 10,000 entries will be 1 at some point. And then no matter what word you choose, the answer will be maybe yes. Also, you need to think about how big you want to make your array. But it's true, the fuller it gets, the higher the false positive rate will be. And I mean, that makes sense now. Eventually, all the bits are set to 1. And that's an interesting thing to think about. And it's useful to understand why using multiple hash functions is better. So imagine you make a Bloom filter where 10% of the bits are turned on, then the false positive rate is about 10%, because you take a random word, you look at a random point in the array, basically, and the chances that it's set to 1 is 10%. So you have a 10% false positive rate. But if you use 2 hash functions, then the probability for that is 10% times 10%, which is a number smaller than 10%, or actually it's 20% times 20%, because you turn on twice as many bits now. And the same for 3 hash functions, so it's 30% times 30% times 30%. But that explains why that curve is going down at the beginning, and then it takes off at the end because you're back into the regime where you've turned on all of your bits. Bloom filters are used for applications where definitively no or maybe yes are good answers. And there's lots of places, if you look around the internet, where people use them. My favorite one probably is people who run content distribution networks, so Cloudflare, things like this. they don't necessarily want to keep every single page that every single person in the world visits in their cache. They might say, actually, we will only keep this in our cache if more than one person visits this thing. So they use a Bloom filter where you enter, when you visit some obscure website on the internet, they check in their Bloom filter, has somebody before you recently visited this site? If yes, we will cache it. And if no, we will not cache it because we don't want to fill up our cache with stuff that is only visited by, single individuals. But you can do lots of other things with them as well. So what if you want to count things? You don't just want to keep track of stuff, but you want to count how many you've seen. So this poor person here works in a fruit factory, and their job is to sit there at the conveyor belt and count how many count the different fruits that go past them. No, they're counting the apples, the oranges, the orange apples. I mean, don't know what AI was thinking when it generated this image. And so on. So that is their job. And again, if you have a very large data set, then you can't just do the naive thing of having a counter for all the different kinds of fruit, or maybe you even have an infinite data set. No? Then it becomes even more difficult. And what you can do is build what is called a count-min sketch, which is, I think of it as putting several Bloom filters together. So every row in this table, you can think of like one Bloom filter. We're using several of them. And every time we see an item, we compute its hash and we go, horizontal. With hash 1, we go horizontally along and set the entry to 1 or add 1 to the entry. And we do this 3 times in this case. And that way we just count things. So next, a red apple, we set, we add 1 to different indices in the array. And then we keep doing this for all the fruits that keep going past us all day long. And maybe we end up with a table that looks like this. So now the question is, how many red apples did you see? What we do is we compute the 3 different hash functions, 1 for each of the rows, look at what the value is there. And what you can see, so in this case, it's 1, 5, and 3. And then the one we report to the person is the smallest number. That's why it's a min. That's what the min in the count min sketch stands for. And the idea is that sometimes it happens that the 2 different fruits will increment the same place in the array. But for different rows, it will happen in different places. So if we take the smallest number, we get the best estimate of what the true number of red apples is. Because, for example, in the second row here, you can see it says 5, and in the example I built, the red apples and the orange apples increment this counter. So that's why we use the smallest one and not the average of them, for example. If you want to build this, it gets a little bit more complicated again than building a Bloom filter. You now have a row per hash function, but otherwise the idea is exactly the same. You compute the hash of your word, you go there, you increment the counter by 1, and if you want to know how many times the word has appeared or the fruit has appeared, then you go and look up the count in each row, and then you take the minimum of the counts that you've seen. And where would you use this? Well, maybe you run a social media network, I don't know, Blue Sky, Twitter, X, Facebook, and you want to keep track of which topics are popular. And there's many topics, and you don't want to have a counter for each one of them. And also, you don't need to know precisely how many tweets there were about, fruit. But what you want to see is that there's vastly more tweets about fruit than about train schedules or something like this. Or you want to find popular items in your web shop or things like this. Okay. Another thing you might want to do is count unique items. So this is slightly different from counting the fruit. What you're interested in is the different types of fruit that are going past you. Also, you want to know, in this picture, there are orange apples, red apples, oranges, strawberries, bananas, and green apples. So 6 types of fruit. And this is useful maybe if you want to count visitors to your website for different categories, so maybe for all the different countries in the world, without storing information about your visitors. Now, you can make up the categories ahead of time, and then you have a counter for each of the countries and maybe each of the browsers and maybe even every combination of countries and browsers. So in that way, you don't have to store any information about the individuals visiting the website, but you still have an estimate of how many people from Switzerland use Firefox to visit my website. And the best intuitive explanation of how to do this that I've found is to think about having to flip coins. So this person here has been flipping coins for a very long time. Now they look quite tired. And if you ask somebody who, you want to estimate how long have they been flipping coins, and maybe they've been keeping track and they have a very big number that they can tell you. But the other thing you can ask them is, what is the longest run of heads? So how many times after another have they flipped head? And that number gives you an idea of how many times they must have flipped the coin already, because now if you flip a coin 10 times, it's extremely unlikely that you will get 10 heads in a row. Or you probably get like 2 or 3 heads in a row, and then you're lucky. But if you flip a coin 100,000 times, I would be shocked if you didn't get at least 5 heads in a row. And you can make a little simulation. Each of these different histograms is how many times you flip the coin, and then you can make a histogram of the longest run of heads, and you can see if you flip a coin for 50,000 times, the longest run, the most likely one is probably something around 15. And the sad thing is that if you flip a coin 1,000 times, the longest run is about 10. So to make progress, you need to flip a lot of coins. If you want to get a run of 20, you probably have to flip the coin very, very many times. So the way this applies to the HyperLogLog, which is the fancy name for counting things, is we compute the hash of all the items that we see. And if you look at it in binary, then it will be 0, 1, 1, 0, 0, 1, some very long string of zeros and ones. And for the more unique items we flip, the longer the number of leading zeros that we will see. Because every time you compute the hash of a new item, you get a new string of zeros and ones. And if the more different things you compute the hash of, the higher the chance that one of them has a very long string of zeros at the beginning. And so that's how the HyperLogLog data structure works. It keeps track of the longest string of zeros at the beginning of the hash that is seen. And then if you ask at some point later, how many unique items have you seen, it does some mind-bending math to turn that into an estimate. And it's mostly math. There's not a lot of coding involved, so I will skip over all the formulas. Okay, so that's the end already. Probabilistic data structures. Bloom filters, super useful if you've got a problem where you need either a definitive no and maybe yes. So it's like a set. Count-min sketch counts items in very, very large data sets. And the HyperLogLog counts how many unique items you've seen. And the selling point for these is that often you don't need the exact answer. You need a good enough answer And then you can use vastly less memory and or make them much faster than using the exact equivalent. So that's when you might want to use these. There's several more of them. There's a whole zoo of these probabilistic data structures. Hopefully, you see that there is no magic involved in using them. And it's, I think, interesting to have a somewhat intuitive idea of why they work. There's, of course, lots of little details that I cheated or didn't tell you about. But you can go and read about them now. You can look at, maybe understand how these super optimized implementations of these algorithms work, because they do all sorts of clever tricks to make them really performant. But the downside of that is that if you don't already know how they work, it's very difficult to work out why they work. All right, this is the end. This is what Nano Banana thinks this howler looks like. I asked it to generate all the images, including this one. I was like, I'm not sure you've ever been to Rapperswil. Thank you very much. We do questions now?
We can do questions now, right? Yeah. Right. So, are there questions in the audience? And is somebody with a mic ready? There. Just raise your hand if you have a question. Yeah. Simon has one.
And I will do it. Is any of that implemented in scikit-learn, or used?
No, but there is a library called Scrub, SKRUB, and they use some of these to deal with very high cardinality data sets. So if you, okay. So the answer is, check out a library called Scrub, which is built by other scikit-learn maintainers. It helps you do pre-processing stuff for your machine learning data sets. But in scikit-learn itself, we don't use them, I don't think.
Okay. But is it implemented in Python? And I think the whole performance issue is gone. Or is it only a wrapper? Do you know that?
So in Scrub, I don't know how they implemented it. I've never investigated. But yeah, there are implementations in Python, of course, but they're not the fastest ones. But there are libraries that have a nice Python interface where there's high-performance C code behind it, or Rust and things like this.
Perfect. Thank you very much.
Are there other questions in the audience? Over there, the left.
Thank you. Just wanted to ask, do you know of any optimization techniques for example, for the size of the Bloom filter to keep the false positive rate and maybe lower the size or things like that? Are there any things to do?
So there are formulas that let you compute the false positive, or an estimate of the false positive rate. So then you type in how many items you have, how much memory you want to spend, and then it tells you what the false positive rate could be. And it also depends on how many hash functions you use. So that's one way of doing it. Another way, I think, is to make a little simulation to try and get an estimate. Because I think there's some... Oh, yeah, that's the answer.
Okay, thank you.
All right. I think we have time for one or two more questions. Do I see any raised hands? Right. Over there, another one.
Right.
Hey, thanks for the talk. I might have missed it. I came a little late. So if you mentioned it, I'm sorry. But at what scale does it make sense for me to start thinking about those things? Because even if I have like 1 million unique items or so, I don't think it's really necessary to think about these probabilistic data structures.
Yeah, I think the time to use them is, for example, I think it's on Reddit, they keep track of the unique visitors to things with HyperLogLog data structures. They have a lot of visitors, but but they also want to keep track of lots of different ones and quickly be able to show the answer without having to query a database. So, or for example, I think if you want to do other web analytics, for example, and you don't want to store information about your visitors in your database for privacy reasons, you could create lots and lots of counters for different categories or cross products of them, and then you quickly end up with a number that's too big to just put in your database. But yeah, for 1 million items, I think this is interesting, but far too complicated.
Thank you.
All right. There's one more question. We would have time, but I think that's it. So thanks a lot again, Tim.
Thank you.
Very good talk.